Hi Honors Math 2. You should have found this task, 8.8, in your module. We see our fourth conic section today. With our new schedule for e-learning that we only meet twice a week, my first hour is supposed to meet on Mondays and Wednesdays, and my 8th hour is supposed to meet on Tuesdays and Thursdays. So from here on out, I'm going to post a Monday-Tuesday assignment. You can do it either day. And then a Wednesday-Thursday assignment. You can complete that either day. So you will have assignments posted twice a week. Alrighty, I'm going to ask you, this is kind of a long task, so I'm going to pause a lot and I'm going to ask you to do some work on your own. Can you please take the next 3, 4, 5 minutes, read the first page of this task, and answer questions 1, 2, and 3, and then come back to us. Okay, when you come back to us, if you look at these two equations for an ellipse and a circle, notice in this ellipse, your A, the horizontal movement, is 4, and B, the vertical movement, is 3, where in your circle, the radius is equal to 4. So for some similarities and differences, you might have said, for similarities, they both have an x squared and a y squared. They both have centers at 0, 0, or some other similarities. For differences, you might say something like the radius of your circle is always 4. So I'm stretched both vertically and horizontally a distance of 4, those equidistant points from the center for a circle. But the ellipse has a horizontal stretch of 4 for that A value and a vertical stretch of only 3 for that B value. So then we get that oval shape rather than those equidistant points all the way around. Alrighty? Okay, question number 2. Good observation, Maya. If she took the equation of a circle and divided through by 16 to write it like an equation of an ellipse, notice then that A is equal to 4 and B is equal to 4, and then my horizontal stretch is the same as my vertical stretch. And even though it looks like the equation of an ellipse, it actually becomes a circle because A and B are the same. And for number 3, you probably noticed that a circle is always an ellipse, especially ellipse with A equal to B. But an ellipse is only a circle if A is equal to B. So this ellipse happens to be a circle where A is equal to 6 and B is equal to 6. All right, turn the page and read for one moment. Okay, as you read a little bit further, Maya then takes this equation of an ellipse that we just saw, and she changes that sign in between to subtraction rather than addition. And she's curious, will this be an ellipse if she changes that to subtraction? And you might start to guess, no. An ellipse always has plus in between equal to 1, and this is not going to be an ellipse. But what will it be? Alrighty, so I'm going to ask you to start to graph this thing that has subtraction in between rather than addition. I don't know any good way to graph this except to start making a table of some values. So I'm going to ask you to pause for a second. If you let x equal 0, take a second and solve for y. Then let y equal 0 and take a second and solve for x. I'm picking 0 just because they're easy things to plug in. Pause and please find the y values and the x values if you let those variables equal 0. Okay, if I let x equal 0, then that first term is gone. Solving for y, I multiplied both sides by 9. Divide through by -1, and y squared equals -9. Take the square root of both sides, and I don't get a real number, square root of -9. So if I let x equal 0, I have no y value. But then I let y equal 0, and then this term is gone. And I've got x squared over 16 minus 0 is equal to 1. X squared equals 16. Take the square root of both sides, and when y equals 0, I get plus or minus 4. So when y equals 0, I get plus or minus 4. It's a little tricky to find some points on this shape, but let's see. I found it was nice when I plugged in 3 into that equation. I squared it, I got 9, because then this is 1. And then I noticed it didn't matter if I plugged in plus or -3, because when I square it, I'll still get 9. So if I plug in plus or minus 3, stop and see what you get. Okay, this is not real pretty, but we'll get a general idea of the shape of this graph. When I plug in y equals 3 or -3, that numerator is 9. Divided by 9 is 1. So I'll have a -1, add 1 to both sides, I'll have 2. Multiply both sides by 9. And I'm right here, that x squared is equal to 18. Take the square root of both sides. And x equals plus or minus the square root of 18 for my decimal approximation. You could simplify that to plus or minus 3 root 2. Alrighty, so when x When y is 3, x is the square root of 18, which is bigger than 4 over here. When x is 3, when y is 3, x could be negative root 18, which would be somewhere over here. If y is negative 3, I also get plus or minus root 18, which is something like this. And we start to get this strange shape, which is our fourth conic section, and it's going to look something like this. Ha! And this fourth conic section has what we call these two branches. We still call these the vertices of this conic section. We'll still have a center of this conic section, and we call this a hyperbola. Our fourth conic section is a hyperbola with these two branches. Okay, you can pause and jot down the definition of a hyperbola. A hyperbola is the set of all points, the difference of whose distances from two fixed points, still called the foci, is a constant. For a hyperbola, I didn't find them exactly, but the foci are actually going to fall inside those branches. And the difference of distances is always a constant. If I pick this point on my hyperbola and take this distance, d1, and subtract this distance, d2, that will be the same as pick another point on your hyperbola, this distance, d1, minus this distance, d2. The difference of the distances from two fixed points is always a constant. Some things are similar between an ellipse and a hyperbola. The distance, I should go this one first, is similar. The distance from center to focus is still called C. In a hyperbola, the distance from center to vertex is going to be A. And then we have to talk about that distance B in a moment. Alright, I don't have a cool hyperbola maker. A hyperbola is a little bit trickier, but I do want to come back to this picture. And some smart cookie even emailed me and asked me last week, how come, Mrs. Ianchek, I use a double cone to get my four conic sections? Well, here it is. If I ever split a cone with a plane, and that plane is parallel to a base, that cross section, if I take the top off, will be a circle. If I take a plane and cut that cone parallel to the slant height over here, that cross section, if I take that left side off, is going to be a parabola. If I ever split my cone so that my plane is not parallel to a base and take the top of that cone off, I'll get an ellipse. And I need a double cone for my fourth final section, where if I split that cone with a plane, that double cone with a plane, so that it intersects both of those cones, and if I could take this right-hand portion of my double cone off, my cross section, if I look at it, is going to be a hyperbola. I'm going to have that double shape. I'm going to have an arc up here and an arc down here, and I get a hyperbola. That's our fourth conic section, all defined in terms of distances and all formed by when a plane intersects that double cone. Alrighty, we're going to try to get through as much as we can today in this 15 minutes that I have. Let's see, so I'm going to try to graph this hyperbola where I make a change where the y squared is first instead of the last case where the x squared was first. Okay, let's see what happens when y is first and then we subtract x squared. Again, plug in x equals 0 and y equals 0 and see what you get. Here's my solution. When x equals 0, I got y squared equals 9. And y equals plus or minus 3, which I can plot. If y equals 0, that first term is gone. I'm left with x squared multiplied through is negative 16. Take the square root, which is no real solution. And then I like to plug in y equals plus or minus 4. Nope. That's backwards. I like to plug in x equals plus or minus 4. And see what you get for y, please. Okay, when I let x equal either positive or negative 4, it doesn't matter. I get y squared equals 18, and y is plus or minus the square root of 18. and I can plot those points. Pause and plot those. When I plot those 4 points, I start to see my hyperbola branches forming. And you can start to see the difference in my hyperbolas when I start with that y squared rather than an x squared. Please pause and notice some of those similarities and differences between what you graphed in number 7 and what you graphed in number 5. I thought for this one, number 7, the y-intercepts are plus or minus 3, but if you turn back a page in number 5, the x-intercepts were positive and negative 4. Here the branches open up down when that y squared is out front, but in number 5 the branches open left right when that x squared is out in front. Take a minute to read this next paragraph, and we're going to label a few things on this hyperbola. Okay, this is pretty cool. We'll start to see the standard equation for a hyperbola looks similar to an ellipse. This denominator is always a squared under that first term. This denominator is always b squared under your second term. In this case, a is equal to 3, and a is the distance from the center of my hyperbola to the vertices. b, in this case, is 4. b is kind of strange. b, I'm going to count to the right 1, 2, 3, 4, and to the left 1, 2, 3, 4. And that paragraph that you just read is talking about this little imaginary rectangle. Over 4, up 3, over 4, down 3. And that rectangle actually forms, this is crazy, the asymptotes, dash them through the center, that hyperbola will follow. C is still going to be the distance from the center to the foci, which fall inside those branches. Take a minute and label those things, and I'm going to label that B. Okay, so jot down a few things if you would. B is that imaginary distance to form the rectangle. So this is my B value. This was my A value. And this was my C value. The diagonals of the rectangle that you've drawn form the asymptotes that the branches for your hyperbola will follow. Take a moment and jot those down. This is a nice little reference right here. Please notice that if x squared is positive out front, your hyperbola will open left-right, like the x-axis is left-right. But if y squared is positive, then your hyperbola is going to open up-down like the y-axis, so that's easy to remember. So whichever is positive out front for a hyperbola tells you the direction of the opening of those branches. And remember, the foci always fall inside your branches. And since those foci always fall inside my branches, for a hyperbola it's convenient because C, the C value is always the biggest. We're going to finish up today with numbers 10 and 11. Okay, we were asked to graph this equation. A is always the first denominator, which is 6. B is always the second denominator, which is 5. The center here, I haven't moved at all, is 0, 0. Start to plot those. I'm sorry, and notice that x squared is first, so this is going to be a left-right opening for my hyperbola branches. A is the distance to my vertices, in this case left-right from the center. My B value of 5 really just helps me to find that rectangle. Where is it? 6, 5, over 6, down 5. There's my imaginary rectangle in the middle. My asymptotes will pass through the middle. It will be the diagonals of that rectangle. And my hyperbola branches will pass through the vertices and follow those asymptotes. We do need to stop for a second and think about how to find C so I can find those foci. I would also like you to find the equations of the asymptotes. Pause. Okay, the equations of my asymptotes: rise 5, run over 6, have a y-intercept of 0, become y equals positive or negative. My slopes are 5, 6, my y-intercept is 0. C is always the biggest in a hyperbola. I'm going to post my notes because we're going to run out of time. Please wrap up this task and then check my solutions that are posted. Have a good day.